In this paper, we present a deep reinforcement learning approach to solving navigation among movable obstacles. First, a bit of brief context about NAMO. In this problem setting, the agent has the ability to manipulate the environment in order to navigate from one point to another. For example, the agent can push a chair out of the way, pull a table backwards, or maybe lift up some small bags or small furnitures. Most of the literature has tackled this problem with some form of search-based methods, but with simplifications such as giving the agent prior knowledge about whether an object can be moved or not, constraining obstacle manipulation in an axial aligned fashion, so either in the X or Y direction. Furthermore, the computational complexities of these methods are often exponential with respect to the number of obstacles. In this work, we tried to address the last 2 points using deep reinforcement learning. We train an Advantage Actor-Critic policy in the NVIDIA Isaac Gym simulator. An example of an environment we're training is shown in the screenshot here, where the robot tries to traverse through the obstacles to the goal position here labeled as blue. A benefit of using neural network is that it achieves constant computational complexity with arbitrary number of obstacles. Our policy also pushes obstacles in non-axial aligned fashions, which is much more realistic. Lastly, we demonstrate that our algorithm is easy to implement on different robots using high-level control outputs, and that physics simulation helps us smoothly bridge the sim-to-real gap. Here in the video, you can see an example of a quadrupedal robot implemented with our train policy. You can see that the robot is able to reason which boxes to push in what order in order to get out of the room. Here we demonstrate a few more examples of the robot solving different kinds of narrow problems locally with different numbers of boxes in the scene. The videos here are played at half the speed so that it's easier to see what's going on. We believe that what we demonstrated in this paper scratches the surface of the full potential that could be achieved using deep reinforcement learning. And in future works, we're going to explore ideas such as how can the robot deal with objects of varying sizes, shapes, or weights, where we hope that the robot can learn in real time how an object moves by interacting with it. We also want to explore the generalizability of the network in different map configurations. For example, perhaps we could put two of these local number problems very close to each other, where the solution of one depends on the other. Another idea we could use is a camera-only input, which will result in an even more flexible policy to be implemented on real robots.